All right, let's talk message tracing. Observability in distributed systems can be annoying. Messages move fast, hop between servers, and when something breaks, it's hard to know where. Most tracing tools make you instrument your code or spin up something external. NATS just has it built in. If you ever needed to debug your system or just wanted to peek under the hood, this one's for you. I'm going to show you how to trace any message through your entire system. We'll cover the CLI command, break down what all that trace output actually means, and then run through a live demo so you can see it in action. Let's go check it out. So yeah, like I was saying, observability in distributed systems can be a pain. But NATS isn't just a messaging system, it's a unified communications layer. So we built tracing right in. No external tool or code changes, just run a command and see exactly where your messages go. That's what's cool about it. So tracing messages in NATS is pretty simple, and we built a CLI command that handles everything for you, the trace command. When you run the trace command, it sends a message through your NAT system to the subject you specify. And once it reaches its destination, you'll receive output that shows the complete path your message took through the system. Here's some example output. Now there's quite a bit of information here, but don't worry, I'll explain it all shortly. If you'd like to skip ahead and start deciphering the trace output right away, feel free to jump to the demo section of this video. We're going to do a quick semi-deep dive, I guess you could call it. When you use the CLI to send the trace command, the initial trace message includes 3 special headers. As the message flows through the system, each node or server sends its own trace message reporting its current progress. First, you have NATS trace destination. This specifies the subject where all the trace messages will be sent. Second, you have NATS trace only. This enables dry run mode. Your initial message is traced throughout the system, but not actually delivered or stored in the end. This is especially useful for tracing without any side effects. And third, accept encoding. This header compresses the trace events. NATS supports both gzip and snappy compression formats. So these 3 headers are automatically set by the CLI when you run the command, and they're sent with your message. So what does this look like in practice? Let's walk through an example with a system setup where we'll publish a trace message to a subject. In this case, we'll have 3 clusters, and each cluster will have 3 nodes or servers. The servers in a cluster are connected to each other, and each of the clusters are connected to each other through a gateway connection. We'll also have 2 leaf nodes connected to the first cluster, C1, and we'll have 5 leaf nodes connected to the third cluster, C3. Now we're going to connect a client to our third leaf node off of cluster 3, and in this instance we have JetStream enabled and subscribed to the subject our trace message is publishing to. We also have 2 additional subscribers listening to the same subject. One of these subscribers is subscribed to a leaf node off cluster 1, and our other subscriber is subscribed to a normal cluster node in C2. Our message will ultimately reach all 3 of these subscribers. First, a temporary inbox subject is created internally to receive all the intermediate trace messages, and this inbox will aggregate all of those messages. So when our trace message is published, it reaches the first server. This server then creates its own trace message and sends it to our temporary inbox. Let's check out what this message actually looks like. These trace messages contain 4 main fields. The server field, which gives us data about the server. The request field, which gives us information on the request made to the server. The hops field, which tells us how many hops are being made from this server. And the events field, which tells us all the events that occurred on the server. There's 2 fields within an event that we need to understand: the type field and the kind field. So let's talk about the type field. Event types basically tell us what happened. Here are the various event types you'll encounter. You have IN for Ingress events, EG for egress events, JS for JetStream access, SE and SI for stream export and import when the message crossed an account boundary, and SM for subject mapping, when the subject was transformed via mapping rules. Now for event kinds. These tell you what type of connection it was. So you can see your usual client, router, or gateway, and you also have leaf node and JetStream. And system and account are internal. Okay, now that we sort of have these legends, let's look at our message and see if we can break it down. First, let's look at the server portion of the message. Here we can see the server name, which is C3L3, our leaf node server. There's also other fields like cluster, and since this is a single leaf node, it's its own cluster. Now onto the request field. Here you can see our three headers. We're using snappy encoding. You can see the temporary inbox destination subject, as well as the trace only header. If we look at the hops field, it tells us there's one outgoing hop from the server. And now finally, the events field. You can see we have two events. Let's check this out in our diagram. So the message made it to our C3L3 leaf node server. And for this event, first we can see it's an Ingress type. We can also see it's a client connection. It also shows you the name of the client. And you can see this matches up with our diagram currently. We published the message from our client and it landed in our leaf node. We also see an egress type that leaves this server. Its kind is 4, which is a leaf node connection. Since we're on a leaf node here, that makes sense. It leaves to go to nodes C3 and 2, which is a cluster node in cluster C3. So this lines up with everything we see on our system diagram here. Cool stuff. Let's keep going. Now that trace message is sent off to our inbox, and the original trace message travels to the next node, server C3N2 in our C3 cluster. And this server sends another trace message to our temporary trace inbox subject. All right, now let's examine this one. You can see this is the C3N2 server that our last message had an egress event to, and it's part of the C3 cluster. Let's check out the request. You can see we have the same headers, but this time we also have a new header, NATS trace hop. So this is a good time to bring it up, that when we perform traces, we're slowly building a routing tree structure. This lets us track the general layout and path our message took throughout the system. The best way to understand this is to look at the hops field and the events field. And you can see here there's 3 hops going out from this server. Under events, we have our Ingress type event of kind 4. Since 4 is leaf node, this makes sense. The message came from our leaf node server C3L3, so everything lines up. Now let's look at the other events. We have 3 egress events, which are the hops from this server. We can see a hop to C3N3, the location of our JetStream stream, which is kind 1. This is a router kind, meaning it's a connection to another node in the same cluster. And you can also see this egress event has hop 1.1. Now check out the second egress event. This one is kind 2, which is a gateway connection. And this makes sense because we're using a gateway connection to connect to cluster 1, server N3. And if you look at the hop, it's 1.2. And now our last egress event. It's another gateway connection. This time it's going to cluster 2. And you'll see that this hop is now 1.3. And now this is how we build our routing tree. Since this server has 3 egress events, it branches out in 3 different directions. We designate this by assigning a number for each hop. Since there's multiple branches, we increment the number. You can imagine if server C2 and 3 also branches out, those 2 events would look like 1.3.1 and 1.3.2 respectively. And that's how we build our routing tree. Let's look at what our message at node C3 and 3 looks like. So the message hit the server and it emitted the trace message, and this is what we get. Check out our NATS trace hop. Here it's 1.1. You can see we hopped once from our leaf node to server C3N2, and then one more time to C3N3. We have this Ingress event from C3N2, which matches up with the router kind 1, and then our only egress event is type JS for JetStream. So this published message gets added to our stream. Notice that there is no hop field because there are no hops from this server. All right, cool. So it all lines up. So you can kind of see how our trace messages trace through our system server by server until they reach their endpoint. Now, I'm not going to keep going with this diagram because I think you get the idea by now. So we're going to actually run this command in a second and see what it does. But when it all finishes up and we finally get our output, the temporary inbox subject goes away. Internally, this output is used to build the very first output message you saw earlier in the beginning of the video. And one last big thing to mention. By default, tracing stops at account boundaries for security reasons. To continue tracing, you have to set allow trace true on imports or export rules. The rule being the receiver always opts in. If it's a stream import, the importer sets it. If it's a service import, the exporter sets it. All right, cool. Let's try running the trace command and do this live, and then we can break down the output. Okay, let's actually run this command now. We're using the exact same system setup as we had before. So 3 clusters, 3 servers per cluster, and some leaf nodes. All right, I'm going to create the stream on cluster C3. And the stream is going to be placed on the elected leader, C3N3. Now I'm going to create two subscribers, one on the leaf node off C1 and one off the cluster node on C2. And now that they're all listening, let's perform our trace. So if I run this command without the trace flag, it will give me the minimal output you saw at the beginning of the video. With the trace flag, it's going to give us the entire trace message that we broke down server by server earlier. All right, time to run it. Boom, that's a lot of text. I took the liberty to copy out and format this top part, and it should look familiar to you. And this is what it ends up looking like. Very, very similar to what we had earlier. But let's check out the formatted output the good folks here at Synadia made for us. And we've come full circle. Here we go. This is the final output we get. So we have this handy dandy little legend here, and you can see the different symbols for connections. We can use this to break things down easier. So we start the client and we publish to our leaf node, C3L3. Then we take a leaf node connection from that to server C3N3. C3N3 is where our JetStream is located and the message is stored in JetStream. We also take two gateway connections from there to C2N2 and C1N1. Then C2N2 takes a router connection to server C2N3, and that's delivered to the connected client. C1N1 takes a router connection to C1N3, which then takes a leaf node connection to C1L2, which is then promptly delivered to that client. And down here you can see we took two leaf node, gateway, router, and client connections, and then one to JetStream. And that's our trace. Pretty neat. So that's all I have for that, but I'll be doing another video in the future on how to utilize this with OpenTelemetry. So stay tuned for that. Hey guys, I hope you enjoyed the video. Drop a like if it helped you out. Let me know in the comments what you'd like to see next. I'm always looking for ideas. And subscribe if you want to see more. Thanks for watching.